we are going to speculate on how we can formulate a way for humans to navigate to Mars using SpaceX Falcon 9. There are 5 main steps to the trip from the surface of Earth to the surface of Mars as follows. Step 1. Stage 1 of the Falcon 9 gets us partway to low Earth orbit, typically about 100 kilometers altitude. This is not a stable orbit and we cannot rest here. Step 2. When stage 1 runs out of fuel, stage 2 of Falcon 9 gets us the remainder of the way to low Earth orbit at an altitude of about 200 kilometers above Earth. Step 3. A Hohmann transfer orbit from low Earth orbit out to Mars orbit. Step 4. A Mars insertion burn to get into a stable orbit above Mars, again about 200 kilometers above the surface. Step 5. Landing on Mars. We will be using some terms which need defined. Delta V is the change in velocity of the ship in question. Delta V has units of meters per second, but because these numbers are typically in the thousands, it is often stated in kilometers per second. Specific impulse. This is a measure of the efficiency of an engine converting fuel into thrust. It has units of seconds, which is not immediately intuitive, however larger is better. Specific impulse is typically improved for engines operating in vacuum rather than an engine operating in atmosphere. For simplicity, you can imagine it is easier for the exhaust to leave the engine quickly if there isn't any air for it to push through. We will be discussing the mass of rockets. This is the amount of material in the rockets. It is like weight, except weight only occurs in the presence of gravity. Mass is not dependent on gravity. If you don't understand this, for mass, read weight. The mass of rockets is typically broken down into 1. The dry mass. This is the mass of the rocket itself. 2. Payload mass. This is the mass of cargo carried by the rocket, often including subsequent rocket stages. 3. Fuel. The term fuel is used as a combination of both the fuel and the oxidizer. Most of the rocket initial mass is fuel. We are not going to explain the rocket equation here. You can look that up elsewhere. The delta V to get to low Earth orbit above Earth is typically stated to be about 7.8 kilometers a second, plus 1.1 kilometers per second to overcome gravity. Initially, as the rocket is trying to go straight up and gravity is pulling it straight down, much of the thrust is lost to gravity, and about 0.5 kilometers per second is lost to air resistance. SpaceX states that Falcon 9 can lift 22.8 tons to low Earth orbit if the first stage is sacrificed, and 18.5 tons if the first stage is recovered, as some fuel needs to be reserved to land the first stage. As we shall see, we need all the delta V we can get for this Mars mission, so we will not be recovering the first stage. The first stage of Falcon 9 has a dry mass of 25.6 tons, a payload of up to 134.5 tons, and can carry 411 tons of fuel. The specific impulse of the Merlin engine on stage 1 is 282 at sea level and 311 at vacuum. As the ship rises in altitude, the air thins and the specific impulse improves towards this 311 figure. For simplicity, we will assume stage 1 spends about 1/4 of its time at sea level and 3/4 of its time at vacuum, and so we can assume an average specific impulse of 303.75. From this we can see that stage 1 can contribute about 3.78 kilometers per second of delta V towards getting the second stage to orbit, at which point the first stage has used up 410.5 tons of its 411 tons of fuel. The second stage now has to do the remainder of the delta V to LEO. The second stage Merlin engine has a nozzle extension optimized for operating in vacuum, and so gets a specific impulse of 348. It has a dry mass of 3.9 tons and can carry 22.8 tons of payload and has a fuel capacity of 107.8 tons. If we use these figures, we can see that Falcon 9 could not in fact lift 22.8 tons to low Earth orbit, as it is just a little short of fuel. The value of delta V to get to LEO must be too high, as we know Falcon 9 can just get 22.8 tons to LEO. If we use a value of 9.2 kilometers a second for the delta V required to get to LEO, the second stage achieves this with 0.79 tons of fuel remaining. We are out of fuel and can go no further. Except we can trade some of the 22.8 tons of payload for extra fuel. Let us initially assume our 22.8 tons of payload is actually 2.8 tons of useful payload and 20 tons of extra fuel. The human transfer orbit to Mars requires 3.58 kilometers per second of delta V. The fuel at the start of this maneuver is the fuel remaining at the end of the previous maneuver. We can complete this maneuver and still have 2.9 tons of fuel remaining. Circularization of the orbit around Mars at about 200 kilometers altitude takes about 2.11 kilometers of delta V, assuming no aerobraking. We do not have enough fuel for this maneuver. If we drop our useful cargo to 0.8 tons, we have the extra fuel for step 4 and still have just under 500 kilograms of fuel remaining. Decelerating and landing on Mars, again assuming no aerobraking, requires about 3.8 kilometers per second of delta V. We can see we don't have enough fuel for this maneuver. Even if we trade all our useful cargo for fuel, we are still short. We can reduce the delta V requirements for the last two maneuvers if we use aerobraking, except the second stage does not have the heat shielding necessary for aerobraking. To add this shielding would add weight. Let us assume about 20% more weight that we need to remove from our fuel or cargo allocation. But by adding this shielding, we can expect to get the circularization delta V down to about 1.1 kilometers per second and the landing delta V down to 1 kilometers per second. This would allow us to get about 300 kilograms to the surface of Mars. Unfortunately, we have also overlooked fuel loss. While most of these stages take place in quick succession, the human transfer takes 259 days, and during this time we can expect some fuel to boil off and be lost. Fuel boil off is a complicated process and the loss is not at a constant rate, but a rough estimate would be that we would lose 1 kilogram of fuel a day to boil off. We would therefore have 259 kilograms less fuel at the start of the circularization burn than we had at the end of the human transfer burn. When we calculate this, we need to drop the cargo to 165 kilograms. One last thing we have not considered is that Falcon 9's second stage does not have landing legs or any altitude sensors related to landing. Let's assume an additional 300 kilograms of dry mass for these. Once again, we can't get any cargo to Mars. Now let's imagine that SpaceX stretched the second stage by 10%. Since the engines don't need to stretch, I'm going to allocate 8% more dry mass and 10% more fuel. This doesn't help us as we have to carry this extra dry mass throughout every maneuver. Now imagine instead we stretched the first stage by 10%. Again, 8% more dry mass and 10% more fuel. We are able to land 149 kilograms on Mars, which might be just enough for an Optimus robot, the solar panels to keep it charged, and a small server to assist it with more complicated operations. However, to do this, we would need to do the following changes to Falcon 9. Stretch the first stage by 10%. Ensure fuel boil-off did not exceed 1 kilogram per day. Add heat shielding to the second stage. Add landing legs and landing controls to the second stage. Instead of stretching the first stage by 10%, imagine that SpaceX managed to improve the specific impulse of the second stage by 2%. This relatively small change allows 207 kilograms to make it to the surface of Mars.